All right, Chemistry 1411. This is chapter 17, which deals with electrochemistry. And to get into the subject of electrochemistry, we're going to do a little review on redox chemistry, and we're going to define what electrochemistry is. Electrochemistry is the study of the interconversion of chemical and electrical energy. Chemical energy, of course, comes from bonds and molecules, so that comes from bonds. And electrical energy, that comes from the flow of electrons. So if we're able to harness the flow of electrons, which you probably know is electricity, we're able to use the electrical energy. So electrical energy, again, that's derived from the flow of electrons. And so in order for us to understand electrochemistry, we have to be able to understand the flow of electrons in reactions. So we're going to look at oxidation and reduction reactions wherein there is a flow of reactions. And oxidation and reduction are, are mutually exclusive. You can't have one without the other. The bottom bullet point says the reactions are characterized by the exchange of electrons from one substance to another, which produce discrete charges like an ion. So something like, if you have a sodium ion, well, it's pretty obvious what the charge is on that. It's got a +1 charge, or apparent charges. And we're going to spend some time looking at apparent charges. And that's what we did last class when we were looking at oxidation numbers. Now, if you just look at this simple reaction that's shown here on the bottom, you see that the zinc is being converted from just zinc metal, right? It says it's a solid zinc, so that means it's just a pure bar of zinc or a rod of zinc or something, and it's being converted into zinc with a 2+ charge. Notice that now it's an ion and it's in an aqueous solution. We also see that copper 2+, which is an ion, is being converted into copper metal. How do I know that? Because the copper 2+ is an ion that's in an aqueous solution, and the copper here is just plain old solid copper, just like copper metal that you'd find in a copper pipe or a copper wire. Well, if you take a bar of zinc, okay, just a rod of zinc, and that's what's shown here inside this beaker, and you put it in a solution of copper 2 sulfate, right? So copper 2 sulfate, right? This is an ionic compound, right? It's made of copper 2+ ions and sulfate ions. So that means we have an interaction in here between the zinc metal, which is in the bar, right, and copper 2+ ions that are in the solution. And what the reaction arrow is telling me here is that if I combine zinc with a copper 2+ ion, I'm going to get zinc ions and I'm going to get copper metal, copper solid. And you see that what happens over time is that zinc bar erodes away. You see that there's less of the zinc bar here. You also notice that the color of the solution has changed, and you can see that there is some solid copper deposited at the bottom. Well, why did the zinc bar erode? Why did it start to disintegrate, if you will? Well, because as the zinc solid is being converted into zinc ions, where's the zinc coming from? The zinc is coming from the zinc metal, so that means the zinc metal is going to disappear. And where is this copper here coming from? Well, when the electrons that were lost by the zinc are gained by the copper 2+, right? I get the copper 2+ is gaining those electrons and forming solid copper on the bottom, and that's what we see down here. So this is an oxidation reduction process. The zinc is being oxidized. We say it's oxidized because it's losing electrons, and you probably remember the acronym oil rig, and I have that somewhere in my slides. Oxidation is losing electrons, and reduction is gaining electrons. So since the zinc lost electrons, and we can see that here, the zinc is going from no charge, right? There's no charge to now it's got a 2+ charge. Well, how do you go from something that is neutral or has no charge to having 2+? Well, it's got to lose 2 negative, right? It lost 2 negative. That means it lost electrons. So we say that the zinc is oxidized. We also call it a reducing agent. Why would I call it a reducing agent? Because it's affecting the reduction of the copper 2+ ions. Let me show you what I mean. Reduction is gaining electrons. That's what RIG, the acronym RIG, stands for. And we see that the copper 2+ ions, how do I go from copper 2+ to copper with no charge? It must have to gain 2 negative, right? It's just simple algebra. If you take a +2 and you add something to it and you get 0, what must the something be? The something must be a -2, and that is the 2 electrons that are gained by the copper. So we say that the copper has been reduced, but we also say that the copper is an oxidizing agent. Why do we call it that? Because it's affecting the oxidation of zinc. And you have to be aware of what an oxidizing agent is, what a reducing agent is, and you have to be able to identify the species that are being oxidized and reduced in redox reactions. And we'll get plenty of practice in that today. And if you're a little rusty on your oxidation numbers in ionic compounds or covalent compounds, well, we'll take a look at that as well. A little bit of history, and I'm not going to spend a lot of time on this. If you've wondered where the terms oxidation and reduction come from, well, reduction comes from a reference, or a reference is the fact that when metals were first purified from minerals, which are normally oxides or sulfides, they're ionic compounds that contain that metal in it. When you take the metal that's in an oxide or sulfide and then you generate the pure metal, what are you doing? You're going to end up removing oxygen or sulfur, and so the mass gets reduced, right? Here's an example. You take this mineral, which is called cassiterite, which is basically tin 4 oxide. So here's the mineral, and then the oxidation number, and I'll go over this with you in a second here. The oxidation number is +4 for the tin, and it goes to 0. So it's being reduced, right? Because it's gaining 4 electrons to give you an overall charge of 0. And if you don't follow me on that, I'll explain it in a second. But the idea is this, is that the mass of tin that you obtain from the metal, from the mineral, right? This is going to be heavier than the amount of metal that comes out, right? So that's why we call it reduction. Nothing more than that. Okay, and you can go and look up the history of that, but if you just wanted to know where the word comes from, there you have it. Okay, let's talk a little bit more about the redox process. I'm sure that many of you are following me by now because it's probably something you've seen before, or hopefully it's something that you saw in General Chemistry 1. You should have, or maybe in high school chemistry or something like that. So again, when we have that transfer of electrons between reactants, we call those redox reactions. Again, you cannot have one without the other. Yes, I know that we have such thing that we call half reactions, but half reactions have to be combined to make a whole reaction, don't they? Okay, so if we have compound A, let's say, okay, up here, and we combine it with compound B, and if compound A ends up losing an electron and giving it to compound B, what's happening is that compound A is actually being oxidized. Now, if you're like, what do you mean by that? Well, I mean that compound A is losing an electron, right? Oxidation is losing electrons. So compound A gets oxidized. Conversely, compound B gets reduced, right? Because reduction is gaining that electron overall. But what happened in the process is what affected the reduction of B? What caused it to be reduced? Well, A caused it to be reduced, and so A is the reducing agent. What caused A to get oxidized? It was B that caused A to get oxidized, and so B is the oxidizing agent. So oxidizing agents gain electrons, they get reduced, like B, and reducing agents lose electrons and they become oxidized like A. Now, I think it's actually easier to look at this kind of thing when we're dealing with real elements and molecules and ions instead of just A's and B's. I actually think it simplifies it a little bit. Again, here is the little memory trick or mnemonic that you can use. Oil rig oxidation is losing, reduction is gaining. That's something I only learned since I moved to the States. In Canada, everybody uses this one. Leo the lion says grr. So loses electrons means oxidation. Gaining electrons is reduction. I'm sure it's used down here too, but that's what I grew up with when I was in high school. That's what they taught me. Leo Zigar, which is French. Anyhow, whatever. So oxidation numbers. I went over this last class with you, so I'm going to cover it really quickly today. But when we're looking at the transfer of electrons in a redox reaction, we have to be able to assign what oxidation numbers are. And an oxidation number is, it's kind of like the pretend charge or sometimes the apparent charge on an atom in a molecule or an ion. Now, when it's in an ion, I think it's easier, right? If you have chloride with a -1 charge, well, it's pretty easy to figure out that the oxidation number is -1. But what if you have a chlorine in, chlorate, for example? Then it gets a little bit trickier. So when we deal with a covalent molecule, like what if you had, I don't know, what if you had ammonia, right? Ammonia, that's a covalent molecule. Well, then also, I would say it gets a little bit trickier than if we just have an ion, like let's say you have, just say you have bromide or something, right? Then it gets, I'd say it's a little simpler then, okay? And how do we decide what the oxidation numbers are? Well, they're based on the electronegativity. And when you have elements sharing electrons, as you do in a polyatomic ion like chlorate, or in a molecule like ammonia, we assume that the element that is more electronegative, and you guys know the trend of electronegativity up and towards the right in the periodic table is where electronegativity increases. The more electronegative element is the one that takes all of the electrons in the bonds. You can assume that all of the electrons are assigned to the more electronegative element. Of course, if you have elements that have the same electronegativity in a covalent bond, well, then they're going to share the electrons equally. Okay, and we'll look at examples of that as well. So here are the rules. I went over them last class. I'll go over them a little bit quicker this morning. So free elements. So any element by itself in the periodic table is going to have an oxidation number of 0. So if you just look up a metal like chromium or vanadium or gallium, you look at a non-metal like, I don't know, antimony or something. Oh, antimony is a metalloid, isn't it? Anyhow, you look at a non-metal like neon, for example, okay? Well, those all have an oxidation number of 0. You need to know the diatomic elements have no fear of ice cold beer. Don't send me any emails saying, Mr. Dion, you shouldn't be talking about beer. I never said it was alcoholic, okay? Last semester, I had a student send me an email, Mr. Dion, you shouldn't be bringing up beer in front of undergraduates. I wrote the student back, I said, there's non-alcoholic beer. Maybe I meant root beer. Don't read in too much into it. So you need to know the diatomic elements. You also need to know that sulfur comes in packets of 4, phosphorus comes in packets of 4, and sulfur comes in packets of 8. So all those free elements have oxidation numbers of 0. If you have a monatomic ion, right, like a chloride or a bromide or a nitride, you just look at the charge on the ion and you know what the oxidation number is, right? Say, for example, you had nitride. It's an ion you should know. That's going to have an oxidation number of -3. Let's say you had oxide, which is O2-. It's going to have an oxidation number of -2. A really quick rule is that any elements in group 1A always have a charge of +1. Any elements in group 2A have a charge of +2. And aluminum is always +3. So aluminum +3 always. And you can remember that because Al always, right? +3. Oxygen, is there another one in here? Where did I have fluoride? Oh yeah, I must have it later when I talk about the halogens. Anyhow, oxidation number of oxygen is almost always -2. An exception would be H2O2. So if you look at H2O, the oxidation number of oxygen is -2. So that means that hydrogen will be +1. But in H2O2, this is -2. And so we have -4. So each one of these would be +2 in that example. There's other examples that I'm not going to get into. You can take a look at it if you want. You have a superoxide. This is called potassium superoxide. That's neither here nor there right now. Anyhow, oxidation number of hydrogen is +1 unless it's in a compound where it's bound to a metal. So you need to know the difference between, right? If you just see hydrogen on the periodic table, we call that hydrogen, and that's a hydrogen atom. If you see H2, that's a hydrogen molecule, right? Hydrogen is a diatomic element. That means it exists as H2 in its pure form. If you have H+, we usually call that a proton, and we saw plenty of those in the acids bases chapter. But if you have a hydrogen with 2 electrons, it has a negative charge, and we call that a hydride. So it has a -1 oxidation number. So whenever you have hydrogen combined with a metal like lithium, sodium, calcium, whatever, we call that a hydride. If you had it combined with potassium, right? The potassium is +1 because it's a group 1A metal. the hydrogen would be -1 in that case. Another good rule is that fluorine is always -1. There are no exceptions to that. Other halogens have negative oxidation numbers when they're in an ionic compound. And an example of that would be something like if you had calcium bromide, right? The bromine is -1 because the calcium is always +2. However, when halogens are combined, and I mean halogens that aren't fluorine, when halogens are combined with oxygens, then they have positive oxidation numbers. Say, for example, you have the hypochlorite. So hypochlorite ion, which would be ClO minus. Well, if the oxygen is -2, that would mean that the chlorine is +1 in this case, because overall we have an oxidation number which is -1. Or say, for example, you had the chlorite ion, which is ClO2 minus, right? If the oxygen is -2 and you have 2 of those, that gives you not -2, gives you -4. Well, -4 plus what gives you -1. So the answer is the chlorine would have an oxidation number of +3. So we see that the oxidation number of a halogen can be positive when it's combined with an oxygen. What else? In a neutral molecule, the sum of all the oxidation numbers has to equal 0. So let's say you had a molecule like ammonia, right? All oxidation numbers, they all add up to a big old 0 because the molecule is neutral. And if you had a polyatomic ion, let's say you had phosphate, PO43 minus, all the oxidation numbers are going to add up to -3, right? Because you have a 3- charge on your phosphate ion. Anyhow, and we looked at those examples right here. So those are the rules for oxidation numbers. We looked at these first two problems on Wednesday. Let's take a look at C kind of quickly. So if I have C, that's potassium chlorate, KClO3. So C is potassium chlorate. Well, since potassium is in group 1A, we know that its oxidation number is going to be +1, don't we? This is going to be, this is going to be +1. And that means that we know that the ClO3 ion, the chlorate ion, is going to have an oxidation number of, a charge of -1 overall. Well, we know that oxygen is almost always -2. So if we have -2 and there's 3 oxygens, that gives us -6. Now, -6 plus something gives us the overall charge of -1. So what would that be? That means that the chlorine has to be +5. So our chlorine is going to be +5. So we've got our potassium, which is +1. We've got our chlorine, which is +5. And we have our oxygen, which is almost always -2. Kind of running out of room here, but the next one is the hydrogen sulfite ion. I'll do this one a little quicker. If I was going to do this one by myself, I would say hydrogen sulfite. I know that the hydrogen is going to overall have an oxidation number of +1. So that means that my sulfite, which I already have memorized, is going to have overall a charge of 2-. Okay. I know that the oxygen is -2 times 3, which gives me -6. I have overall a charge of -2, which means that my sulfur must be +4. So my hydrogen is +1, my sulfur is +4, and my oxygen is -2. And those are the oxidation numbers of those elements in the hydrogen sulfite ion. So there you go, a little bit of practice with oxidation numbers. Well, now let's take a look at some examples where we look at oxidation numbers and we try to determine who is being oxidized and who is being reduced. Before we answer this question, I just want you to be aware of one more thing about oxidation numbers, is that oxidation numbers don't always have to be whole numbers. They can actually be fractions. I asked a question to my organic chemistry students about that this winter. Back in, when the semester first started, I gave them some exercises where they were doing a little review of general chemistry too. And I asked them about oxidation numbers, and they had forgotten, or several of them had forgotten, that oxidation numbers can be fractions. And if you noticed, we haven't looked at a ton of oxidation numbers with with respect to carbon in General Chemistry 1 or really in General Chemistry 2. But if we look at this molecule right here, this is propane, the same propane that's in your propane barbecue tank or anything you have that's propane powered. Well, if I know that hydrogen is always +1, unless it's combined with a metal, and carbon is not a metal, if I have +1 and I have 8 of them, that gives me a total charge of +8. So what times 3 is going to give me -8? So you can just express this as a fraction, and the oxidation number for the carbon must be -8/3, right? If you take -8/3 and you multiply it by 3, what do you get? You get -8. And so the oxidation number of the carbon is -8/3. I like to express it as a fraction. If you want to work it out in a calculator, be my guest, but I wouldn't bother doing that. Next, our oxygen. Who could tell me what the oxidation number of the O2 is? What would the oxidation number of the O2 be? Yeah, it's 0, right? It's its pure form. So the oxidation number of the oxygen is 0. In carbon dioxide, my oxygen is going to be -2, right? Because oxygen is always, almost always, -2. Excuse me. And if I have -2 times 2, that gives me -4, which tells me my carbon must be +4. My oxygen here is -2. My hydrogen here is +1. So now we can figure out who's changing oxidation state. So who's being oxidized and reduced. You can see there's no effect on the hydrogen, right? It goes from +1 to +1. So we can just forget about that. But we see that the carbon is going from negative to positive, right? -8/3, which is around -2.7, to +4. That means it must have lost electrons, right? Remember, what do you guys call oxidation is losing. So this is oxidation, right? The carbon is being oxidized. Who's being reduced? The oxygen is being reduced because it's going from 0 to 2-. So this is reduction, okay? Now, if the carbon is being oxidized, what's the oxidizing element? Remember, the carbon is being oxidized, so the oxidizing element, okay, is the element that's affecting the oxidation. Well, what element is being reduced? And the answer is oxygen. They also ask you, what's the oxidizing agent? The oxidizing agent is the agent that has the oxygen in it, which would be O2. Next, they ask for the reducing element. So reducing element. Again, oxygen is undergoing the reduction, and so carbon is affecting its reduction. The carbon is being oxidized, so it's affecting the reduction of the oxygen. And they're also asking us for the reducing agent. What's the reducing agent in this case? It's the whole molecule that possesses the carbon, which is propane, C3H8. Give me a thumbs up if you follow me on that one. If you're not lost, you're like, you know what, I need to practice it, but hey, I think I can do it. Okay, so I want you to, let's not worry about the question because I asked too many questions in this one. I don't like questions where you ask 6 different things. I want you to tell me what's being oxidized. Could anybody tell me what element is being oxidized in this reaction? Give you a second to think about it. Yeah. Yeah, the cadmium is being oxidized. Could anybody tell me what element is being reduced in this reaction? Yeah, silver. Okay. If you're wondering how my students figured that out, what's being oxidized and what's reduced? Well, the cadmium is in its pure form, and so it has an oxidation state of 0. In silver chloride, chloride always has a charge of -1 unless it's combined with oxygen, and it's not. And so my silver must be +1. If I look at cadmium, cadmium 2 chloride, well, my cadmium has a charge of +2, my chloride has a charge of -1, and my silver in its pure form is 0. There we go. So now we figured out the oxidation numbers of everything. You see that the chloride remains unchanged. It's -1 and -1. So we don't have to worry about that. But the cadmium, the cadmium, where is it? Not Cadbury. The cadmium is going from 0 to 2 plus, right? It's losing electrons, and therefore it is undergoing oxidation. So this is oxidation. And the silver is going from a +1 to a 0. That means it must have gained electrons, right? So this is reduction. Okay, let's take a look at another one. We'll take a look at the next one kind of quickly. And of course, I have the answers to these posted on Canvas. Let's just take a look at C. I have ammonia plus oxygen gives me nitrogen and water. The elements that are in their free state, you could just, put a 0 on top of those very quickly. We know that hydrogen is going to be +1 because it's not combined with a metal. Same thing here, it's going to be +1 because it's not combined with a metal. That means that our nitrogen is going to have to be -3 because there's 3 hydrogens. And our oxygen is going to be -2, and we kind of knew that anyway because we've looked at water already. So what's happening here? You see the nitrogen is losing electrons. Now, if you're unsure about that, if you have -3, right, plus something gives you 0. Well, that means that it must be losing 3 negative charges. Sorry, I should have not put that as negative. Let me put it like this. -3. But subtract something, and the answer would be -3, right? So you're losing 3 electrons in order to have a charge of 0. And our oxygen is going from 0 to -2. So it's gaining electrons, and so it's being reduced. So this is reduction. This is our reduction, and this is our oxidation. All right, I'm going to leave you, D, for you to take a look at that on your own. Actually, you know what? I have one question for you. Could anybody tell me what the oxidation number is of the iron that I just circled in blue? Yeah, it's +3. Okay, good. I just want to see if you guys could answer that quickly. Right? You know that oxygen is -2, and there's 3 of those, so that gives you -6. I need to have +6 over here, but there's 2 irons, so that means that each one is +3. So this is iron 3 oxide, right? So the iron is being reduced. It's gaining electrons because it's going from +3 to 0. And then the carbon is being oxidized because it's going from +2 to +4. Anyhow, again, I'll leave you that one to take a look at on your own time. Give me a thumbs up if you're like, yeah, I think I got oxidation reduction. I'm cool with that. I'm cool with oxidation numbers, or at least, I can figure it out after a little bit of practice. It's normal to have to practice. Everybody has to practice oxidation numbers, right? But it's rewarding because I think that once you have the rules down pat, usually students are pretty rock solid on it after they've had a little bit of practice on it. Well, for the next 4 hours, I want to take a look at balancing some redox equations in aqueous solution, because this is a really important technique that you are going to be asked about on your next exam. You're going to be asked about it on your final exam. If you're the kind of person who's interested in writing an MCAT or a DAT or a PCAT or a HESI exam, well, maybe not a HESI exam, but if you have a standardized exam in your future, and you all have a final exam in your future, right, in this class, you are going to want to know how to balance redox reactions in aqueous solution. And what's interesting is that these are oftentimes complicated because we have to analyze them using what's called the half reaction method. And we also have to be able to balance them in acidic or basic conditions. Okay, if you go back to what you learned in Chemistry 1401, and I know that a bunch of you were in my class in Chemistry 1401, we talked about balancing reactions. Absolutely, we did. When we did titrations or limiting reactant problems, we had to have nice balanced equations. But if you remember, if you were in my class, when we talked about titrations, I had one slide and I just mentioned it really quickly. I said, hey, you guys, this is an example of what's called a redox titration. And you might remember, maybe not, but I had this really crazy balanced equation. And everybody was like, whoa, what is that? And I said, don't worry, you don't have to learn how to balance that until general chemistry 2. Well, today is the day where you learn how to balance redox reactions in acid and base. Now, I want to preface this by saying that if you look around, if you are the kind of person who likes to peruse the internet and you try to Google solutions to some of the problems in the book, or maybe you're looking up extra problems or something, you will find different ways of solving these problems. Now, obviously, they're doing the same thing because you always get the same answer. But if you are just learning it, it can look really different when you look at, the different ways that are done, okay? Now, I have a really, what I call sort of my shorthand method way of doing it, and I'm going to show it to you, and we're going to spend some good time this morning practicing it. But here's what you do. You're given a redox reaction like this one here, and they want you to balance this in acid. So when you're in acid, you're going to have H plus, right, protons in the environment. And if you're in base, you're going to have hydroxide in the environment. The first thing you're going to do is you're going to separate the half reactions, the oxidation reaction and the reduction reaction. You can obviously see that this is oxidation of iron 2, right? Because you're going from a 2 plus to a 3 plus, so it's losing electrons. The next one, you have to be Johnny on the spot with your oxidation numbers, don't you, right? You have to be able to say, well, oxygen is minus 2 times 7, which gives me negative 14. So that means if I want to have a 2 minus overall, I've got to have plus 12 over here. But there's 2 chromiums. So that means the chromium is going from plus 6 to plus 3. So it's gaining 3 electrons, right? You've got to be able to write down the oxidation numbers correctly and identify who's being oxidized and who's being reduced. So the iron 2 plus is being oxidized, and the chromium is what's being reduced. Okay, so that's the first step. You can write them down in whatever order you like, doesn't matter. I like to write down the oxidation first, but you'll probably, notice that sometimes I screw it up, or not screw it up, but I'll write down the reduction first, depending on how quickly I'm thinking. Anyhow, next, what you're going to do is you balance every element that's not hydrogen and oxygen. So balance everything and forget about hydrogen and forget about oxygen. In the first one, we have 1 iron and 1 iron. Good, no problem. Even though they have different oxidation numbers, the elements are still balanced, right? Here we have 2 chromiums, and in the reduction, we had only 1 chromium, so we need to put a 2 in front of that as a stoichiometric coefficient. Okay, so now the irons are balanced, son of a gun, and the chromiums are balanced. Next, you're going to balance the oxygens first using water molecules. So since you're doing it in an acidic solution or a basic solution, well, if you're in acid, there's obviously water around there, right? Acid's going to be a solution in water. Now, there's no oxygens here to even worry about, so forget it. Over here, we have 7 oxygens on this side, and we have 0 oxygens on this side, so that means we need to add 7 water molecules to balance out the number of oxygens. You can still see that neither reaction is perfectly balanced in terms of charge and stoichiometry. So let's move on from there. The next step is to balance out the hydrogens. And what do you use to balance out hydrogens? Well, when you balanced out oxygen, you used H2O. When you balance out hydrogen, you use protons, H plus ions. Now, again, this one here, there's no hydrogen, there's no oxygen. So, hey, nothing to do, right? But over here, we had 7 water molecules. 7 times 2 gives you a total of 14 protons. That means we're going to need to put 14 protons over here. We're still not done. Next thing you do after you've balanced out the hydrogens is you balance out the charge using electrons, okay? So we balance out charge using electrons. If you look at this reaction here, we have +2 on one side, we have +3 on the other side. If I just tack an electron on this side, that means that I have +2 over here, +3 plus -1 gives you +2. So it's all balanced out. If we look at the next reaction, we have 2 times 3 plus, so that means we've got +6 over here. Here we've got 2 minus plus 14 plus, which gives you +12. So +12 and +6 aren't balanced. I need to add 6 negatives, right, plus a -6 to give me +6, which is the same as this. Where do I get negative from? From electrons. So I need to add 6 electrons to this side. Give me a thumbs up. I don't like to stop in the middle of something, but give me a thumbs up if you follow me thus far. We're almost at the end, I promise. We're getting very close, okay? All right, we got one more thing to do. The very last thing you're going to do is add the 2 half reactions together. But the problem is you can't add them together the way that they're written right here. You add them such that you can cancel out the number of electrons. I got 1 electron in the first reaction and 6 in the second reaction. So what I'm going to do is I'm going to take this entire oxidation reaction and I'm going to multiply the whole dang thing by 6. So that way I'll have 6 electrons as a product. I have 6 electrons here as a reactant, and it'll always work out that way. Watch what happens. You multiply those, and then you tally them up, okay? You add them all up. Now, my ledger here is a little bit screwy, but you can see that the 6 electrons here cancel out with those 6 electrons there, and you can't see the margin here. Oh, crumb. Oh, I didn't have it zoomed out. My bad. Anyhow, you see that the 6 electrons cancel out, and you tally it up, and you end up with your balanced redox reaction. Now, beautiful thing about redox balancing is that you don't have to wait for it to be graded. You don't have to put your answer in a computer and just, cross your fingers and say, boy, I hope my answer was correct. Just look at it. Is everything balanced? Let's check. I've got 2 chromiums here, 2 chromiums here. I've got 14 total hydrogens over here. I've got 14 total hydrogens here. I've got 6 irons. I got 6 irons. How many oxygens do I have? I've got 7 over here, 7 over here. Those are balanced. Now I check the charges. What's the charges? Over here I have -2 plus 14 positive plus 12 positive. So that gives me plus 24. And on this side over here, I have 2 times 6 positive. Or 2 times 3, which is 6 positive, plus 6 times 3, which is 18. So I get 24 positive on both sides. It's all balanced out. Beautiful. I love things in science that you can check by yourself. You don't have to wait for somebody else to grade it for you. You can grade it yourself. So it can be frustrating because when you can check yourself, that means that if it's not right, you have to go back and fix it yourself. But anyhow, I digress. Well, with that in mind, let's see if we can use the half reaction method to balance this redox reaction in an acidic solution. Let me just go over here. So I'm going to write sort of a quick and dirty summary over here on the right-hand side of the page. So first we're going to balance the half reactions. So half reactions first. Then we're going to we will balance elements, okay, except for hydrogen and oxygen. We will not balance those. Then we're going to balance oxygen with water molecules. Then we balance hydrogen with protons, balance charge with electrons. Then we multiply the equation so that we have the same number of electrons in each one. So multiply if required, okay? Then we're going to add the reactions and then cancel anything that can cancel on each side, okay? That is my quick and dirty method right there. You can take a screenshot of that, put it on a mug, maybe a beach bag or something, okay? But that is kind of my quick and dirty method. Now, if you're wondering, Mr. Dion, when are you going to get the basic solutions? We'll get there in a second, okay? We'll get there in a little bit. But let's just start out with acid because in base, there's one extra step. Well, if we look at this reaction here, I'm going to go quicker on my oxidation numbers. I go from 0 to +2. I go from my nitrogen, or sorry, my oxygen is always -2, and it's -2 here. So here I have a +2, and here I have a +5. So what's being oxidized? My copper is being oxidized. Maybe I'll put it more in the middle here. Copper is being oxidized to copper 2+. Okay, let's do this half reaction first. Okay, we're going to worry about the NO3- to the NO second. Let me just fix this. Maybe I've never done it this way with students before, but this might be easier. So there's my half reaction. The elements are balanced, right? There's one copper on each side. There's no oxygens to worry about. There's no hydrogens to worry about. Hey, we're already on the last step. This is my kind of chemistry, right? So now we need to add 2 electrons on this side, right? Because I had +2 and I have 0 over here. +2 and a -2 gives you 0. So now my charges are balanced. So now you've done that half reaction. I like it when a plan comes together. Now let's do the nitrate. So we have the nitrate ion, which gives you NO. Okay, the element nitrogen is balanced. That looks good. Next, we need to use water to balance out the oxygens. Here I have 3 oxygens. Here I have 1. I need 2 more on this side, so I'll add 2 water molecules. Now we need to balance out the hydrogens. I've got a total of 4 hydrogens over here. I've got none on the other side, so I'm going to put 4 protons over here. Now I'm going to evaluate the charge on each side, right? I need to evaluate the charge on each side. Well, if I look at this side, I have +4 and -1. So that means I've got +3. And on this side, this side, I have 0. I got nothing. So which side am I going to add electrons to? To the left-hand side or the right-hand side? Will I add my electrons to the left-hand side or the right-hand side?
Left.
Yeah, exactly, right? And you might think, oh, that's a silly question, Mr. DeYoung. Well, you know what? Sometimes, even at this point in your chemistry career, students get confused by adding electrons because electrons are negative. So you're adding a negative. So you're going to put 3 electrons over here, and walla walla bing bang, that is balanced. Those are 2 beautiful balanced half reactions. I cannot add them together in this form, can I? I have to take this one and I'm going to have to multiply it by 3, and I'm going to have to take this one and I will have to multiply it by 2. Why? Because in both cases I'll end up with 6 electrons in each one, and I want to cancel those. So now I'm going to have 3 coppers produces 3 copper 2+ ions plus 6 electrons. My other equation is going to be 6 electrons plus 4 protons. 8 protons plus 2 nitrate ions produces 2 NO plus 4 H2O. And now I'm just going to tally those up. Look at this. It's a beautiful thing. My 6 electrons cancel out on each side. Nothing else cancels. It's a Metallica song. And so I put that all together and I get 3 copper. And now I'm going to put in my phases of matter because, you know, we should. Plus 8 protons, which are aqueous, plus 2 nitrate ions, like that, produces 3 copper 2+ ions, all right, plus 2 NO, which is a gas, plus 4 H2O, liquid, like that. Is that a thing of beauty or what? All right, there's nothing more satisfying than balancing a redox reaction. Well, there's also nothing more discouraging than noticing that after you've printed or posted your slides, you find a problem or a mistake in one of your slides. And I try to minimize my mistakes, but hey, I'm a human being. And there's a mistake in the solution to this. So we're going to skip this one for now, and we might come back to that one later. But I wanted to take a look at another couple of examples with you guys before we just shove on from there. So just give me, I need to find a Taylor Swift blank space. And I thought we would try a couple of the problems from the textbook. What time is it? 10:15. Let me spend 10 minutes on that, and then we'll talk about base after that. So let's try. This is from OpenStax, so straight from your textbook. Do not look at the solutions manual. Right? That's not going to help you. You want to bang your head against the wall until you get it right, right? So we're going to look at question 4A from your textbook. So you have hydrogen peroxide plus tin 2 plus produces water plus tin 4 plus. Well, it's pretty easy to figure out what's being oxidized, right? The tin 2 plus is being converted to tin 4 plus. So that's my oxidation reaction. My reduction is occurring when hydrogen peroxide is being converted into water like that, in that half reaction. So yeah, I wonder if this will work. Yeah, there we go. So there's the patented method. So we got the half reactions done. Next, we're going to balance the elements. Both tins are balanced. There's nothing that isn't hydrogen or oxygen in the next one, so that looks good. Next, we're going to balance oxygen. There's no oxygen or hydrogen here in the first one anyway. The next one, we have 2 oxygens over here, and we only have 1 here, so we'll put a 2 in front of our water. We could have added another water molecule, but H2O plus H2O gives you 2 H2O, which I'm sure you could figure out. Next, we want to balance the hydrogens. Here we have 4 hydrogens. Here we have 2 hydrogens, so we'll put 2 protons over here. And next, we need to balance out the charges. On this side, I have positive 2, and on this side, I have positive 4. So I'm going to need to add 2 electrons over here for my oxidation. Here I have plus 2, and here I have 0. So that means I'm going to have to put 2 electrons over here like that. Now, both of these are balanced, and I can tally them up because the 2 electrons are going to cancel out on both sides. Now we end up with H2O2 plus tin 2 plus 2 protons produces tin 4 plus 2 H2O. Now I'm going to do something that I don't do a whole lot of in this class, okay? Something that I don't do a lot of is I don't stop and get you guys to try to solve problems without me, kind of going over it. And I would like to give you 3 minutes to take a look at a problem. And do not look at the solutions manual. If I take lead 4 oxide plus mercury, and I get mercury 2 plus lead 2 plus. I'm going to try to not say anything for a couple minutes. I hate doing that, but I want you to try to balance this one on your own, okay? And we're going to do it in acid. So I want you to try to balance this redox reaction. So this is in acid, or H+. And just to be sure that I won't talk, I'm going to go grab a quick drink of water. So is anybody finished this? I'll put it to you this way. I know it's too long an answer for you to just, just spit it out. But on this side, we end up with some protons. Could anybody tell me how many protons you end up with on the reactant side when this is balanced in acid? Anybody able to figure that one out? Yeah, you end up with 4. Yeah, okay. All right, let's take a quick peek at it, and then we'll take a look at balancing some redox reactions in base. So we have our lead 4 oxide, right? We know the oxidation number of the lead here is +4, and here it's 2 plus. This is 0, and it's going from 0 to +1, right? Because there's 2 mercury. So anyhow, so let's put our oxidation reaction, which is HG. HGTV gives you mercury 2 plus, like that. We could balance that one first. We need to put a 2 in front of the mercury in the reactants because I have 2 mercuries over here. There's no oxygen to balance. There's no hydrogen to balance, but we need to balance the charge. We need to put 2 electrons over here. So that one's done. Let's take a look at the lead reaction or the reduction. So we have lead 4 oxide, PO2, produces Pb2 plus. I'm going to move that over to make a little extra space here. Okay, the lead is balanced. Next, we're going to balance the oxygen by using water. So we're going to need 2 water molecules over here. We're going to balance the hydrogens with 4 protons over here. Now we need to balance the charge. Over here I have +4. Over here I have +2. So that means I need to add 2 electrons to the reactant side. So 2 electrons over here. And you can see that I have 2 electrons here and 2 electrons here. So I can tally up these reactions with no multiplying. So the 2 electrons cancel. Nothing else is going to cancel. And you end up with lead 4 oxide plus 2Hg plus 4 protons gives you Hg2 plus the lead 2 cation plus 2 water molecules, like that. So to balance a reaction in base, all you want to do is add one more step at the end. Okay, so what I'm going to do is I'm going to copy this, and I want to take a look at an example from the book first instead of the example that's in my slides. So I'm going to copy this and move it down here. And when you're in base, what are you going to do? I want you to balance it the same way that you did in acid. Okay, do the exact same thing that you did in acid, except when you're in base, the H plus that you end up with, you add an equivalent number of protons on each side of the reaction to cancel out the protons. So you add same number of hydroxides to each side to cancel H pluses, the protons. Now, you're only going to have protons on one side of your balanced redox reaction. So you're going to cancel the protons on the other side, right, to make water, because H plus OH minus gives you H2O. And then on the other side, you're going to have hydroxide. If you're not sure what I mean, let's take a look at an example. If you have aluminum plus CrO4 2 minus, which produces aluminum hydroxide plus Cr chromium O4 or OH4 minus. Now, let's take a look. Let's start by writing out the oxidation reaction, which is aluminum gives you AlOH3, right? You're going from 0 to +3, so that's oxidation. Let's start by balancing out the aluminum. That's done. We'll balance the oxygen with water. So that means we need three water molecules on this side. So 3 H2O. We need to balance out the hydrogens. I have 6 hydrogens here. I have 3 here. So that means I need 3 protons over here. And I have a charge of 0 over here. I have 3 plus on this side. So that means I need to add 3 electrons. So now my oxidation half reaction is totally balanced. Let's do the same thing with the reduction. We have our CrO4 2-, which gives you this, there we go, this chromium hydroxide. I'm going to move it over a little bit to make sure I have enough room here. So the chromiums are balanced. That's fine. We have 4 oxygens on each side, so we don't need to add any water. But on this side, I have 4 hydrogens, and on the other side, I have 0 hydrogens. So now I need to put 4 protons over here. Looks good. Now, over here, I have a charge of -1. Over here, I have 2 positive, so +2. So what do I have to add to +2, or how many negatives do I have to add to +2 to get -1? I have to add 3 electrons over here. Okay, now you can see that the number of electrons work out. I don't have to do this step. I don't have to multiply anything. Now I can just tally up those reactions. So I'm going to do that. I'm going to add those together. You see that the 3 electrons cancel on each side. You notice that you have 3 protons here and you have 1 proton over here. So all of these are going to be gone, and you're going to cancel 4 of those and be left over with 1 proton at the end. When you write out your balanced redox reaction, and again, we balanced it in acid first, we end up with aluminum plus the CrO4 2- ion plus H plus, a proton, plus 3 water molecules, hopefully I won't run out of space here, produces aluminum hydroxide plus CrH. There we go. Shit, that's not right. Pardon my language. There we go. Okay, so now we're at the very last step. Now we're going to add the same number of hydroxides to each side to cancel the protons. There's only 1 proton in the entire thing, and it's right here. So we're going to add 1 hydroxide on this side, and we're going to add 1 hydroxide on this side. When I combine H plus and OH, what do I get? I get H2O. So now instead of having just 3 H2O, I'm going to have 4 H2O on that side. And I get that my aluminum plus CrO4 2- plus 4 H2O produces aluminum hydroxide plus the chromium hydroxide ion plus hydroxide. So that is the reaction balanced in base. If we look at, we have 1 aluminum, we have 1 chromium. We tally up the number of hydrogens. We have 8 hydrogens over here. Look, we have 3, 4, and 1. So that's 8 on both sides. Tally up the oxygens. We have 4 plus 4, which is 8. Here we have 3 plus 4 plus 1, which is 8. So those balance. We check out the charge. We have 2 minus total on this side. We have 2 minus total on this side. And that is our redox reaction balanced in base. Give me a thumbs up if you follow me on the concept of adding the hydroxide at the very end. Everybody with me on that? Cha. All right, good. Well, let's try one more, and then we'll call it a day. It's Friday. Rebecca Black is celebrating somewhere. I'll go back to my slide presentation here. All right. You guys knew who Rebecca Black is, or does that date me? Is she too old? I don't know. Anyhow, let's give this one the old college try. Okay, so there we go. Use the half reaction method to balance the following reaction in basic solution. Okay, so we're going to use the same method that we used the last time, and we're going to give it the old college try. So let's start out by writing out the two half reactions. So we have our, sorry, I cannot see. There we go. I need a new prescription so bad. Anyway, forget it. So let's balance this one using the half reaction method. My carbons are balanced, my nitrogens are balanced. I need to put a water molecule over here to balance the oxygens. Now I've got two hydrogens over here, so I'm going to need to put two protons over here. On this side, I have -1. On this side, I have +1. So how many electrons am I going to have to add over here? I'm going to have to add 2 electrons, right? Because +1 plus -2 gives you -1. Everybody with me so far? And if I make a mistake, stop me, because I've been known to make mistakes. I'm human, just like everybody else. Okay, does that look reasonable to everybody? Anybody see any big mistakes in there? No? Okay. I don't see anybody saying there's mistakes, so let's move on. We've got the MnO4. Oops. MnO4 minus ion, which gives you manganese 4 oxide. You know, I like to try to write that reaction arrow towards the middle of the page, just so I have enough room on each side to scribble down whatever I want. Just a little trick when you're doing these, you know, and you're trying to work quickly. The manganese is balanced on both sides, so that's good. We've got 4 oxygens over here. We got 2 oxygens over here. That means we need to add 2 water molecules over here. Now the oxygens are balanced. I've got 2 hydrogens over here, none on the other side. So I'm going to put, did I say 2 hydrogens? I meant 4 hydrogens. So it means I need to put 4 protons over here. Now over on this side, I've got a total of +3. On this side, I have a total of 0. So that means I need to add 3 electrons to that. So that looks reasonable. Now, I can't add these reactions together, can I? I have to multiply the one on top by 3 in order to get 6 electrons, and I have to multiply the one on the bottom by 2 in order to get 6 electrons. So now let's write down the new reaction. So we've got 3 H2O plus 3 cyanides gives us 3 CNO minus plus 6 H plus plus 6 electrons, like that. The one on the bottom, I have 6 electrons plus 8 protons plus 2 MnO4 minus gives me 2 manganese 4 oxide plus 4 H2O. Everything look good? Just double checking here. So when I tally all that up, these two, what can I cancel on each side? The 8 electrons are going to cancel on each side. I've got 3 water molecules here. I've got 4 on this side. So I'll lose 3 of them and only end up with 1 water molecule there. I'm going to cancel all of these 6 protons. I've got 8 over here, so I'll be left over with 2 protons. So now let me write everything down very carefully. I've got 3 cyanide plus 2 MnO4 minus plus 2 protons gives me 3 CNO minus an isocyanate plus 2 MnO2 plus H2O. Like that. Okay, There we go. Now in the last step, I'm going to add the same number of hydroxides to each side. So I have 2 protons, so I'm going to add 2 hydroxides, and I'm going to add 2 hydroxides over here. These two are going to combine to give me 2 water molecules, which is going to cancel this one out and leave me with 1 water molecule on my reactant side. So my final balanced equation will be 3 cyanide plus 2 MnO4 minus plus H2O gives me 3 CNO minus plus 2 MnO2 plus 2 hydroxides. Like that. Hot dog, we have a wiener. That is a beautiful balanced redox equation. You can double check, but I've already checked it. So there we go. Well, that's a lot of time spent on balancing redox equations, but I think it's an important enough concept that we spent some serious time in class looking at it. Again, you're going to be asked to do this on your next exam. You'll be asked to do this on the final exam. If you look around the internet, you'll see several ways of doing it. Again, I think the easiest thing to do is to use the method that I'm using here. Brogan, anything that's the same on each side is canceled, right? So since I have 2 protons plus 2 hydroxides, overall that gives me 2 water molecules. And I also had a water molecule over here. If you have 2 water molecules in the reactant side and 1 water molecule in the product side, this one cancels. You cancel one of these, so you're left over with only 1 water over there. All right, there we go.